Okay, sorry for that interruption. Somebody came in the room. I had to stop recording. There it is. All right, so we were talking about units. So, gas units or gas pressure units have kind of interesting stories about how they were derived. 1 atmosphere is defined as the pressure exerted by the atmosphere at sea level. All right, so that's what 1 atmosphere means, and that's just one of the ways of measuring gas pressure. That there's another unit called the millimeter of mercury, and this is a very old unit from like back in the late 1800s when they first started doing experiments around these kinds of things. Whoops. Um, the way you measured the pressure of a gas was how far it could push a column, a thin column of mercury inside a glass tube, and 1 atmosphere, or the atmosphere, the pressure at sea level, was able to elevate a thin column of mercury in a glass tube 760 millimeters. And so that's how the millimeter of mercury unit came to be. 1 atmosphere is the same as 760 millimeters of mercury. There's another unit called well, I said Pascal up here. It's really called a kilopascal, or thousands of pascals. And 1 atmosphere is the same as 101.3 kilopascals. And then there's a fourth unit called a torr, and interestingly, it has the same basic size as a millimeter of mercury. So 760 torr is the same as 1 atmosphere, which is the same as 760 millimeters of mercury, which is the same as 101.3 kilopascals. So you can do interconversions between all these different pressure units using these little equations right here. So write those down, and they better end up on your resource card for the exam. There's this concept of standard temperature and pressure, just because it's convenient to have a standard um, uh, definition, sort of a convention for talking about gases. And so the chemistry powers that be decided that we would define standard temperature and pressure as 0 degrees C and 1 atmosphere. This is abbreviated STP. And it's just a conventional way to talk about the standard temperature and pressure. So it's just a definition. If you say STP, you know that means 0 degrees C and 1 atmosphere. Let's look at a couple sample conversion problems for those pressure units. So if you had 80 atmospheres of hydrogen gas and you need to convert that measurement into kilopascals, how would you do it? Well, you'd look at those conversions that you saw on the previous slide and you would say, well, 80 atmospheres. I know that there are 101.3 kilopascals in each atmosphere. So I'll set up a conversion factor of 101.3 over 1 and cross out units like we like to do and see that the answer is 8,104 kilopascals. Pretty straightforward. Why don't you try one? Convert 130 kilopascals back into millimeters of mercury. So take a look at the previous slide or your notes or whatever, and come up with a conversion factor that will let you get rid of units of kilopascals and find units of millimeters of mercury. I'll wait. Okay, so here, 130 kilopascals times this conversion factor of 760 millimeters of mercury for each 101 kilopascals gives you 975 kilopascals. All right, so you're going to need to convert back and forth between different pressure units in our gases unit here. So be ready. Now, another thing that's important when you're talking about gases, as I said earlier, is temperature. Pressure, temperature, and volume are the three things that you need to characterize a gas. We talked about pressure. Now let's talk about temperature. And we're going to introduce a new temperature unit called the Kelvin. It's kind of a cool unit, no pun intended, because there's no temperature that's lower than 0 degrees Kelvin. In fact, you can't get to 0 degrees Kelvin. That's because the Kelvin scale was developed to measure kinetic energy. Remember a few slides back, we defined kinetic energy as the energy of movement. If something is moving, it has kinetic energy. So 0 Kelvin is defined as that temperature at which molecular motion stops. And we've never been able to accomplish that in the lab. I think the lowest temperature accomplished so far is about 0.1 Kelvin. So really, really cold, but still not technically the point where molecular motion stops. Kelvin, since it's defined in the way that it is, this scale lets you connect temperature and kinetic energy directly. So the Kelvin temperature of a substance is directly proportional to how much kinetic energy it has. All right, and the Kelvin is useful in gas equations and gas calculations because a lot of times the calculations that we do require you to divide by the temperature. Right? And just sort of mathematically speaking, if you had a temperature of 0, you would be dividing by 0. And you know from your math class that dividing something by 0 is illegal. I'm not sure exactly what happens when you try to divide by 0. I think maybe the universe explodes or something really horrible happens. So you can't divide by 0. And so the Kelvin unit is handy because you never have a 0 degrees Kelvin, and so you'll never be dividing by 0. That'll come back up again when we get to our gas laws unit, our gas laws lecture tomorrow. Anyway, all right, so to convert between degrees C and Kelvin is quite simple. Because the size of the unit is the same, they just start at a different place. So to find the degree in the temperature in Kelvin, you take the degrees in C and you add 273. And to find degrees centigrade, you take Kelvin and subtract 273. That's all there is to it. All right. So let's do a couple conversions. What is 25 degrees centigrade expressed in Kelvin? Well, you saw on the previous page. Look back at the previous page. Okay, what do you get? You should get Kelvin equals centigrade plus 273. So 25 degrees Kelvin is 298 K. What about 400 Kelvin? How do you express that in degrees C? Again, look back at the previous slide. Do the math. You should get centigrade is 2 Kelvin minus 273, so 127 degrees C. Okay, you need to be able to do those conversions, those Kelvin to centigrade conversions quickly and easily. So that's another good candidate for putting something on your note card. Okay, so we've talked a little bit about gases. Let's talk a little bit about liquids. Like gas particles, so gases, the particles in a gas are, I guess I'm not really talking about liquids yet. I need to wrap up gases, don't I? Gas particles are far apart from one another compared to the other states of matter. And the gas particles, whether you're talking about atoms or molecules, the particles in a gas don't interact very much, and there aren't a lot of intermolecular forces between gas particles. Liquids are kind of like that in that the liquid particles can move past one another quite easily, but they do experience intermolecular forces. In other words, the liquid particles are much closer together than the gas particles were, and so those molecules or atoms are able to exert forces on one another. Gas particles don't do that because they're far apart from one another. So this makes liquids act a little differently than gases. That's what makes liquids cohesive, and that's what gives the liquid its ability to change its shape. As you know, if you pour a liquid into a container, it takes the shape of whatever container you put it in. That's because the liquid particles are able to move past one another and assume the shape of their container, unlike a solid. All right. So changing the state between gas and liquid, the terms we use there are, one of the set of terms that we use is vaporization and evaporation. So this is kind of a vocabulary piece. Vaporization is the conversion of a liquid to a gas. All right. So conversion of a liquid to a gas. And evaporation is a special kind of vaporization. Evaporation is where the liquid converts to a gas just at the surface when the liquid is not boiling. All right. So if you've got a beaker full of boiling water, it's not evaporation that's happening as the steam is coming off the beaker. It's vaporization. You see the difference? Evaporation is just what happens at the surface of the liquid when the liquid is not boiling. It's kind of going on all the time. There's a small amount of liquid that's being converted to gas right at the surface of the liquid all the time. That's not vaporization, that's evaporation. That's the difference between these two vocab terms. And now to get a gas back to a liquid, it's called condensation. All right, condensation is the conversion of a gas to a liquid. And you've all experienced that if you ever had a glass of cold water sitting on the tabletop at home and the outside of the glass gets wet. That's because water vapor in the air is condensing onto the very cold ice water glass. Okay, we want to talk a little bit about boiling because liquids can boil. That's something that they can do. There's this concept called vapor pressure. All right. Now, I just mentioned a second ago, even it doesn't matter what temperature it is, there's a little bit of gas that comes off of a liquid. All right, at the surface of a liquid, there's always a little bit of evaporation going on, and so there's a little bit of liquid. For example, in a glass of water sitting on the tabletop, um, most of the water there is liquid, but at the just at the surface of the liquid, there is a gas phase. A very small amount of that liquid water is actually evaporated to be a gas right above the liquid layer, and you can measure the pressure there, the contribution of that gas phase, and that's called the vapor pressure. So if you had a closed system, you're going to have evaporation. You know what? That's a mistake. This should say evaporation. Evaporation and condensation are ongoing at the surface of a liquid, and some molecules of the liquid will be turning into a gas, and some molecules of the gas will be turning back into a liquid. That's what we mean by equilibrium. So there's this kind of back and forth between the gas phase and the liquid phase. That's what's called vapor pressure. And the definition of a boiling point might not be quite what you think it is when you put a pot of water on the stove and you put some heat under it and then bubbles start forming in the water and steam comes off. You say, hey, it's boiling. Well, kind of. But the temperature at which that happens has a kind of more specific definition. The boiling point, the boiling point of a liquid is the temperature where the vapor pressure, right here, equals the atmospheric pressure. So the higher the atmospheric pressure, the higher the vapor pressure must be in order for the liquid to boil. What does this mean practically speaking? Well, think of a place really high like Denver, that's over a mile high in altitude. The atmospheric pressure is less there than it is here in San Diego at sea level. And so that means water will boil at a lower temperature in Colorado, in Denver, than it does here in San Diego. And that's not a big change, it's a pretty small change, like maybe half a degree. But it is different, and that's because of the way boiling point is defined. All right. Okay, now we're going to touch on solids, and that's where we are now. Solids, the molecules of a solid are locked in place, so they don't slide past one another like liquids do. They don't randomly bang around a container like gases do. Remember that billiard ball example that I gave you? That's not how solids work. The molecules of a solid are all bonded to one another and they're locked in place. So the intermolecular forces are holding a solid together. That doesn't mean that the molecules don't move, though. They vibrate. So even solids have kinetic energy. The molecules of the atoms are still moving, they're just not moving around. They're vibrating instead. All right, so that's what that's about. And then there's this process of, so you're familiar with the concept of a phase change in solids. If you have ice, for example, and the ice melts and turns into a liquid, that's one kind of change. And if you take a liquid and you make it cold, it turns into a solid. We're all familiar with that. It's also possible, though, for a solid to go directly to a gas without becoming a liquid first, and that process is called sublimation. Sublimation. You may have seen this happen if you've ever played with dry ice. Dry ice is solid carbon dioxide, and you create it by putting carbon dioxide gas under a great deal of pressure, and that forces it to turn into a solid, and that solid, of course, is very cold. And if you put a piece of dry ice on a countertop, it will give off carbon dioxide gas, but it won't turn into carbon dioxide liquid. So that's an example of sublimation, where something goes directly from a solid to a gas. All right, so this actually touches on the reading that we're going to be assigned probably tomorrow. On page 347 is this picture of a phase diagram. I want to walk you through this a little bit. A phase diagram is a way of looking at comparing the pressures and the temperatures relationships for a given compound. This is kind of a generic phase diagram. It's not for any specific compound, but there is a phase diagram for water, and there's a phase diagram for acetone, and there's a phase diagram for benzene, and there's a phase diagram for sodium chloride. Any compound has a phase diagram. This is a generic one, if you will. And a phase diagram lets you look at temperature. So there's temperature on the x-axis, and notice it's degrees Kelvin. So it starts at 0, where molecular motion stops, and it goes up from there. The temperature goes up along the x-axis, and and pressure goes up along the y-axis. So you've got increasing pressure on the y, increasing temperature on the x. You'll notice that at sufficiently high temperature but low pressure, the compound is a gas. All right, so as the temperature goes up, if you keep the pressure relatively low, then your compound can be a gas. On the other hand, if you keep the temperature relatively low but the pressure goes up, in this section here we have a solid. All right, and then at the right combination of higher temperature and higher pressure, you can have a liquid. So you see how the graph is broken up into 3 sections. There's a solid section, a gas section, and a liquid section. And the lines that separate these things are points on the pressure temperature combination. All right, so what we want to note from this graph is that there's this idea of a triple point. The triple point is where the solid, liquid, and gas phase all exist at the same time. So you can have, for example, a glass of ice water has a triple point. That's because there is solid ice, there is liquid water, and there's that vapor pressure directly above the liquid that I told you about a couple slides back, where there's a little bit of gas phase above the liquid. So a glass of ice water is an example of a compound at its triple point. And the critical point is the point beyond which the liquid can no longer, there can no longer be a distinguishment between the liquid and the gas phases. So the critical point is for sufficiently high pressure and temperature that liquid can't actually exist anymore, or gas, they're indistinguishable. And that's what you can get from a phase diagram, is the different a given phase diagram is going to look different for different compounds, and you can compare the phase diagram of of water to that of benzene, for example, and they would look slightly different. One last slide lets us kind of summarize the phase changes, or the changes in the states of matter between gas, liquid, and solid. And so if you have a gas, it can condense to become a liquid, and a liquid can evaporate to become a gas, or vaporize if it's boiling. If you have a gas, it can go directly to the solid phase by a process called deposition. I didn't really mention that earlier, but here it is now. That's just going from a gas directly to a solid. And then I did mention sublimation, where a solid goes directly to a gas. And then finally, there's a solid that melts to become a liquid, and a liquid solidifies to become a solid. We actually could also call this last one freezing. That's probably a more familiar term, where a liquid turns into a solid. That's called solidification or freezing. All right, so that wraps up our lecture on the states of matter and the phase changes between those states of matter, and we will talk about gas laws next time. Thank you.